In this video, I will introduce the second part of the fundamental theorem of calculus. I will give the statement and show an example, and I will leave the proof for the next video. I remind you that the fundamental theorem of calculus provides us with connections between definite integrals and antiderivatives, two concepts that are defined separately, but that are related through this theorem. And it has two parts. It's actually two theorems. The first part, which we already know, tells us what we can say about any function defined as an integral, and the answer is that it is going to be an antiderivative. The second part of the theorem, which is the point of this video, tells us how can we quickly compute a definite integral, and it's going to be through antiderivatives. So let's focus on this second part. Here is the precise statement of the theorem. Let a and b be real numbers, a less than b, and I take a function f that is continuous on the interval ab. It must be continuous. This theorem tells me how to compute the definite integral from a to b of f. And what it specifically says is that first take any antiderivative g of f. And then the definite integral will simply be the antiderivative evaluated at b minus the antiderivative evaluated at a. That's it. This theorem doesn't tell me how to find an antiderivative. And for some functions that will be easy, for some functions that will be hard. That's a different problem. But if we have a way to find an antiderivative, this will allow us to compute the definite integral very quickly. It certainly is much faster than computing the definite integral from the formal definition in terms of upper sums and lower sums and so on. There is a piece of notation associated with this theorem that we use a lot, and is the following. Since we will often be writing something like this, g of b minus g of a, we can rewrite it or abbreviate it this way. G of x, a vertical bar, on top x equals b, on bottom x equals a. And this just means take the function g, evaluated at b, minus the same function evaluated at a. And sometimes we also write it simply like this. G of x, vertical bar, on top b, on bottom a. This final notation is a little bit ambiguous, but we tend to use it a lot if there is no ambiguity in specific cases. So let's see an example of how this works. I want to calculate the integral from 1 to 2 of x squared dx. First, I need to find an antiderivative. And for this function, I can simply guess. The function x cubed over 3 is an antiderivative. We can check it. The derivative of x cubed over 3 is 3x squared over 3, which is x squared. Yes, it works. And then I have to evaluate it at 2 minus evaluate it at 1. This is why this notation is useful, because first I find the function and then I indicate now I have to evaluate. So that is 2 cubed over 3 minus 1 cubed over 3, which is 7/3, and we are done. You see, this is much faster than trying to compute this integral from the definition or even from Riemann sums. Of course, this leads to the question, how do we compute antiderivatives of very difficult functions? And that's where the integration methods come in, which we will learn later. But for now, there is a lot of functions whose antiderivative is easy. So here is a collection of examples, exercises for you to practice to make sure you understand this theorem. I've chosen 4 integrals where the antiderivative is simple. The antiderivative can be obtained by guess and check, and you don't need anything else, nothing sophisticated. So see if you can try to use this theorem in these 4 examples and you get the same answer. I've given you the answer so you can check it. Next, we need to prove the theorem, and that will be on the next video.